In this video, we continue looking at different types of electrophilic aromatic substitution reactions. Here we are going to look at a reaction that we could consider to be a cousin or a sibling of the last reaction we looked at, which was Friedel-Crafts acylation. Now we're going to look at Friedel-Crafts alkylation. So in the Friedel-Crafts alkylation reaction, as the name implies, what we are going to be doing in the reaction is replacing one of the hydrogen atoms from the aromatic ring with an alkyl group that is going to be donated from an alkyl halide. The catalyst in this reaction, just like the catalyst in the Friedel-Crafts acylation reaction, is aluminum trichloride, AlCl3. So let's go ahead and take a closer look at this reaction. So as a reminder of the general mechanistic steps that we've looked at throughout our unit on electrophilic aromatic substitution, I've put that reminder up here in the upper left-hand corner, just like in previous videos. So what we will react here is we are going to start, for this example, with benzene. We will react it with isopropyl chloride. So I'll put that chlorine atom there on the middle carbon of the 3-carbon chain. So we have isopropyl chloride and aluminum trichloride, AlCl3, fulfilling the role of the catalyst in this reaction, just like aluminum trichloride was the catalyst in the Friedel-Crafts acylation reaction. So let's go ahead and begin by forming a stronger electrophile, pretty analogously to how we went about forming a stronger electrophile in the case of the Friedel-Crafts acylation. So first step here, form a stronger electrophile. So in order to do this, what we will do is take our isopropyl chloride, or whatever alkyl halide we are working with here. We'll react it with our aluminum trichloride, AlCl3. I'm going to abbreviate that rather than drawing out the full Lewis structure of it. Each of those 3 chlorine atoms, by the way, would be directly bonded to the aluminum. And then what we will do is show our chlorine acting as the nucleophile using a lone pair of electrons to form a bond to the aluminum. This is completely analogous to how in our Friedel-Crafts acylation we had the chlorine from the acyl halide come over and form a bond to the aluminum as well. So let's go ahead and draw out what results from that. So we will have our chlorine atom from our isopropyl chloride. So this was our isopropyl group, our chlorine, and then one of those 3 sets of lone pair electrons from the chlorine is coming over to form a covalent bond to the aluminum. So I'm going to show that in red, and then I'm going to go ahead and sketch out my aluminum trichloride, AlCl3, like so. Plug in my formal charges, which is going to work out to be a negative charge on the aluminum, positive charge on the chlorine. And now at this point, what is going to happen is that we will break the carbon-chlorine bond, which is relatively weak, in order to create a carbocation. So we break that carbon-chlorine bond right here. That's going to result in the formation of a chlorine atom that has no formal charge, in other words, a relatively stable chlorine atom, as part of that AlCl4. And then the other product of that reaction, so we broke this covalent bond right here and we took the electrons from it over onto the chlorine, that's going to result in this carbon right here no longer having an octet, and so therefore it's going to have a positive formal charge. So let me go ahead and draw out that carbocation that resulted from breaking the carbon-chlorine bond. The other product of this reaction step is going to be aluminum tetrachloride, AlCl4 right here. Still have a negative formal charge on the aluminum from that, but the chlorine atom right here no longer has a positive formal charge. It would have no formal charge, and so that's why I'm just writing that out as AlCl4 there. So now that we've created a carbocation, we have recognized time and time again throughout the last semester and a half or so that carbocations are strong electrophiles. And so we've created this excellent electrophile here as a result of this first chapter of our reaction, where we had our alkyl halide chlorine attack the aluminum trichloride, and then we broke away the leaving group, the chlorine atom there. We've seen chlorine time and time again being a good leaving group to give a carbocation there at the second step of this business about forming a stronger electrophile. Now that we have formed a stronger electrophile, I'm going to zoom out a bit as we continue onward here into the second part of the reaction, where the pi electrons from the aromatic ring are going to attack the electrophile, that is the carbocation in this case, in order to yield the rhenium. So we have our pi electrons attacking the electrophile to yield the rhenium. Let's go ahead and draw out our aromatic ring, our benzene. Then we can take any of the pi bonds there that we want. I'm going to draw the hydrogens out around this pi bond right here so that we can illustrate what's happening. It is not essential to show those hydrogen atoms, but you can if you want to. Carbocation acting as the electrophile. And so what's going to happen here is that the pi electrons from one of those carbon-carbon bonds of the aromatic ring comes over, forms a covalent bond to the carbocation electrophilic carbon. That's going to yield, as a result of this step, the rhenium intermediate. Drawing my pi bonds here. Drawing my hydrogen, hydrogen, and on one of those two carbons, doesn't matter which one, you will have your new bond to the carbon atom. So I'm going to show that new bond in red, and that was to the middle carbon of a 3-carbon chain. So it's going to be like so, attaching an isopropyl group onto our ring. And we will have our positive formal charge right here of this so-called rhenium. Rhenium is anytime you have this 6-membered ring with 2 sets of pi bonds and then the carbocation right here. So that's our least stable of the intermediates. And what we will do then to stabilize the system and finish off this reaction is restore aromaticity, as we have seen occurring time and time again when we are doing these types of EAS reactions. So third step is that we lose a proton to restore the aromaticity. Just following this pattern that we've been developing all along of this reaction type. So I'm redrawing my rhenium. Draw that isopropyl group on there. Draw my hydrogen over here. Include my carbocation formal charge right there. And then what do we use as the base here? Well, we mentioned earlier that the aluminum chloride acts as a catalyst, meaning that its concentration has to stay constant, which implies that if we use it up at one step of the reaction up here at the beginning, we have to regenerate AlCl3 at the end in some way. And so what resulted from our first phase of the reaction here was we generated aluminum tetrachloride, AlCl4. And so what we can do in order to convert that back to aluminum trichloride, acting as the catalyst, is that we can use one of the chlorine atoms from aluminum tetrachloride to act as the base to deprotonate our rhenium acid here. So drawing out AlCl3, I'm going to draw just one of the bonds to chlorine explicitly here so we can illustrate what's happening. We had a negative charge on the aluminum up here, so we still have to have that negative charge down here. So I've drawn out that bond explicitly, and what we are going to do is have that chlorine via this bond here act as the base, meaning that it's grabbing a proton from the rhenium acid, forcing the carbon-hydrogen bond to break. Those electrons have to go somewhere. They come over to restore the aromaticity to the ring, and that is going to create our final product here, 6-membered ring, conjugated pi bonds all the way around, hydrogen here, and now at this position we would have just our isopropyl group. And it doesn't matter, by the way, where these pi bonds end up in the ring, as long as they are all conjugated. So I could have put the pi bond here, here, and here instead, because in the actual scenario, these are all delocalized by resonance. And so as long as they're conjugated, they can be anywhere within this ring. And so this is our final product of this particular reaction, is that we've replaced one of the hydrogen atoms from the aromatic ring with our isopropyl group in this Friedel-Crafts alkylation reaction that involves a carbocation intermediate. So we need to tackle one additional feature of this reaction that makes it have a little extra plot twist relative to the other EAS reactions that we've talked about so far. And that plot twist results from the fact that we have a carbocation intermediate here. And one thing that we've learned about carbocation intermediates time and time again is that they are prone to rearrangements. If we can take a secondary carbocation and do a rearrangement to make it into a tertiary carbocation, that is going to be a favorable thing to happen. So in the case of the Friedel-Crafts alkylation reactions, those are not immune to carbocation rearrangement. So we're going to illustrate a scenario where you would have to contend with a carbocation rearranging during the course of the reaction. So for this example, let's start with benzene reacting with propyl chloride, or we could also refer to this as 1-chloropropane, and aluminum trichloride as the catalyst. We'll go through the mechanism for this reaction and work toward predicting the final organic product, keeping this concept of rearrangement in mind as the plot twist here relative to the other reactions that we've talked about so far. So first things first, we are going to create a stronger electrophile, a good electrophile for this reaction. So in order to do that, we follow the same template that we've been doing all along, which is we take our alkyl halide, react it with our catalyst, aluminum trichloride, AlCl3. What is going to happen here is that we form a covalent bond between the chlorine and the aluminum over to here, like so. And I will show in red our new covalent bond between chlorine and the aluminum from the aluminum trichloride AlCl3, like so. Just like in our earlier examples, that's going to result in the aluminum taking on a negative formal charge. Chlorine, we can calculate a positive formal charge there. And now at this point, we can consider one possible scenario. If we follow the template that we have looked at previously exactly, what would happen now is that we would break this carbon-chlorine bond, the chlorine is the leaving group, and that would give us, as our product, a carbocation right here. This would be a primary carbocation. Primary carbocations, though, are super unstable. So unstable, in fact, that their formation is not going to generally be possible unless there's resonance or something to stabilize that. And so in this case, there's no resonance to stabilize that primary carbocation, and so that is going to be an unfavorable route for the reaction to take. And so I'm going to put a big X through that. We do not want to make a primary carbocation. Primary carbocations are unstable. That is one of the holy grails of organic chemistry, is don't make a primary carbocation unless there is some way to stabilize it by resonance. And so what can we do here? Are we at a dead end for this reaction, or what's the workaround here? Well, chemistry tends to find a way to work around challenges. And so what happens is that rather than this leaving group just leaving to give a primary carbocation, instead there will be a rearrangement that occurs as well in order to create a secondary carbocation instead of a primary carbocation, since the secondary carbocation is more stable and hence able to form and exist. So whenever we're doing a carbocation rearrangement, it's always going to occur in a way that will take a less stable carbocation, which in our case would have been a primary carbocation, which we're not even going to show the formation of, and instead make a secondary or tertiary, more stable carbocation intermediate. So in this case, what we can do is, as that leaving group is leaving, the chlorine is leaving, we will have one of these two hydrogen atoms shift over to become bonded to the carbon at the end right here. And by moving this hydrogen that I'm highlighting over, that's going to result in this carbon being the location where the carbocation forms, and that's a secondary carbocation, so that's more stable. And so based on the electron pushing arrows that we've shown, what we end up generating is an isopropyl carbocation rather than the primary propyl carbocation. So we've moved, just to recap and make sure that we're on the same page here, or on the same screen here. So CH2 is right here. If we move that proton here, or hydride rather, since it has the lone pair of electrons coming with it, it's referred to as a hydride, we move that over. That CH2 is going to become CH3 at the end. So this would be a CH3 at the end. So therefore no formal charge there. And then the carbon in the middle would be just a CH, because we took one of the two H's and brought it over to here. And so that makes this the location of our carbocation. And that is indeed a secondary carbocation. And so that is going to be the preferred route for this reaction. So as we are creating that stronger electrophile, we have to keep in mind the principles of carbocation formation, and that is we never form a primary carbocation. It's super unstable, so instead do a rearrangement rather than making that primary carbocation to create a more stable intermediate here. So I'm going to zoom out so that we can jump in to the second part of this reaction mechanism, which is now that we have created our electrophile, now what's going to happen is that the pi electrons from the aromatic ring are going to attack that electrophile that we have created. So I will go ahead and draw out my aromatic ring, and from here on out, this mechanism is going to be completely identical actually to the one that we were just looking at for Friedel-Crafts alkylation using isopropyl chloride, because by rearrangement we've generated this isopropyl carbocation here. So we have our aromatic ring reacting with our secondary carbocation right there. We're going to do that reaction via taking a pair of electrons from the pi bond, bring those over to attack. That's going to result in the arenium intermediate, where we have temporarily disrupted aromaticity to form that new bond between carbon and another carbon. So this is going to be another way that we can make a new carbon-carbon bond. The Friedel-Crafts alkylation and Friedel-Crafts acylation are really valuable for that reason, that they yield the formation of a new carbon-carbon bond. That's going to leave a positive charge right here of our arenium. So we've made our arenium, as is the theme for all of these EAS reactions. And then finally, as our third and final step of this reaction, or third and final chapter of this reaction, is that we are going to restore aromaticity by removing a proton. So we're going to remove, or lose, as I could call it, a proton from the arenium to restore the aromaticity. And this is that beta elimination type reaction. So I bring in, redrawing my positive charge here of our arenium, bringing in a base to carry this out, and keeping in mind the aluminum trichloride acts as a catalyst. We need to find a way to regenerate that catalyst from the aluminum tetrachloride that we had present at the end of the first bit of this reaction, where we were generating our electrophile. We had also created up at that step, as I'm drawing in now, the aluminum tetrachloride, AlCl4. By breaking that carbon-chlorine bond right here, we've released aluminum tetrachloride. So now we need to figure out how to take that aluminum tetrachloride and convert it back to aluminum trichloride. So I'm drawing my aluminum tetrachloride down here at the bottom. We have AlCl4 with one of the chlorines shown out explicitly here so I can show what's happening with that. And what will happen here is, in order to restore the aluminum trichloride, we're going to take that bond from aluminum to chlorine. We're going to use that chlorine as our base to grab a proton from the acid right here. That forces the carbon-hydrogen bond to break, those electrons to come back in, and restore the aromaticity of this system. So I'll go ahead and write out our product here. Regenerating the aromatic ring. You can put the pi bonds anywhere in that ring as long as they're all conjugated to one another. Attach that isopropyl group. And I'm going to show the hydrogen there that I had shown over here. Still recopying that. You don't have to. It's implied that it is there. And then the other product of this reaction is that we can illustrate that we have restored the catalyst AlCl3 because we broke that aluminum chlorine bond, and that resulted in releasing the aluminum trichloride here. So we'll finish this particular video with one more example problem of a Friedel-Crafts alkylation reaction that includes another permutation of a carbocation rearrangement that you might observe. So let's go ahead and try to write out the mechanism for this reaction and predict the final organic product of it. So first thing first, in keeping with our theme, is that we are going to generate our electrophile. So I'm redrawing my alkyl halide reactant. It is going to react with the aluminum trichloride, the aluminum acting as an electrophile that is drawn toward the negatively polarized nucleophilic chlorine, comes over, forming a bond to there, to our aluminum. I'm going to redraw my alkyl group. redraw the chlorine that it was bonded to. Chlorine still has 2 sets of lone pair electrons. The third set of lone pair electrons has become a bond to the aluminum. So I'm going to plug in AlCl3 like so. That is going to result in there being a negative formal charge on the aluminum, positive formal charge on the chlorine, and then at this point, this is where we generally have the leaving group leaves, meaning the chlorine leaves. And in this case, what's going to happen is if the chlorine leaves, that would create straight away a secondary carbocation. Secondary carbocations can form. And so what is going to happen here is that the chlorine leaving group leaves. So at this step, the general rule is that the leaving group chlorine breaks away to yield a secondary or tertiary carbocation. It is only in the case of if the leaving group were to break away and yield a primary carbocation where you have to have that simultaneous rearrangement occur at the exact same time as the leaving group is leaving, because it's not possible for that primary carbocation to exist. That primary carbocation being the one we saw in the last example. So when the leaving group leaves here, if we can make a secondary tertiary carbocation, we're going to go ahead and do that as its own step. So we're making this secondary carbocation, and that works out because we've seen in a bunch of different examples of SN1 reactions for one case where we could see secondary carbocations existing happily or relatively happily. So we'll go ahead and draw that out. So we now have aluminum tetrachloride, AlCl4. And we have our secondary carbocation. Now that we have made our secondary carbocation here, we do need to keep in mind the fact that carbocations that are secondary are subject to rearrangement, just like when we're doing nucleophilic substitution SN1 reactions. And so what will happen here is that our secondary carbocation is going to rearrange. And I'm going to zoom out just a little bit so that I give myself enough space to write this out, that our secondary carbocation will rearrange. And this step is going to only occur if it's possible to do a 1-2 shift to give a tertiary carbocation. If doing that 1-2 shift by moving a methyl group or a hydrogen over by one position will not give a tertiary carbocation, the step will not happen. The step is only energetically favorable if we can take a secondary carbocation, like we have here, and convert it into the more stable tertiary carbocation. So in the particular example that we are looking at here, indeed, we do have the ability to rearrange this carbocation into something more stable, because if we take the hydrogen atom that is right here that I just drew in blue, and we do a hydride shift where we move that over by taking its bond over to here onto the adjacent carbon atom. So we're doing a 1-2 shift because we're moving spot 1, meaning carbon number 1, over to carbon number 2. In that 1-2 shift, what's going to happen is that now this carbon right here that was originally a CH now becomes a CH2. And the carbon that was right here that originally had 4 covalent bonds to it, once it loses that hydrogen, it is only going to have 3 covalent bonds. So now this is where the positive charge will reside. And so I'm going to put a plus in there to indicate that is the location of the positive charge. So don't forget to do a carbocation rearrangement if you make a secondary carbocation and realize that you can do a 1-2 shift to give a tertiary carbocation. The rules for doing those 1-2 shifts are the same as what we've dealt with throughout Organic 1 and Organic 2 so far in reactions such as SN1 type reactions. So now we've completed the first phase, if you will, of the electrophilic aromatic substitution reaction, which is where we create the strong electrophile. Now that we've created that strong electrophile, specifically meaning our tertiary carbocation intermediate, they just circled in green there. Now what we'll do is use that as the target of our pi electrons from the aromatic ring. So now going into the second chapter here of EAS reactions, what is going to happen is that one of those sets of pi electrons comes over, forms a covalent bond to the carbocation like so, and that's going to disrupt aromaticity, at least temporarily, to give this rhenium. We have seen a lot of rheniums so far. So I'm just drawing out my rhenium, get my double bonds all in there, here and here. And we had 2 hydrogens originally bonded there and there, so I'm going to draw those just to keep track of where everyone is. We had our new covalent bond to the alkyl group, which I'm highlighting that new covalent bond in blue here in our product side. And I'm going to draw out that alkyl group. So at the position that's directly connected to the aromatic ring, we have 2 methyl groups there. So I'm going to methyl group, and then a 2-carbon chain additionally. So we'll go like so. And just highlighting what we have connected here. So we had, based on my pink highlighter, here, that was corresponding to here and here in the final product. And then we also had this additional 2-carbon chain right here and here, and that's the 2-carbon chain coming here and over to here. So we have that exact same group that I've drawn in pink here, drawn over here and connected via the blue bond that corresponds to the electron pushing arrow that we used to generate that bond. Now, one last essential point here, put in the positive formal charge on our rhenium. And so we would describe this as that second part of the reaction mechanism where our pi bond from our aromatic ring attacks the electrophile to give us our rhenium intermediate. And then down to the home stretch here, last part of this is going to always be the deprotonation step, where we're going to lose a proton to restore aromaticity through that deprotonation step of our aromatic intermediate. Okay, so we draw our rhenium, boom, 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 draw my pi bonds in there, trying to get it right here. I'm just redrawing it exactly like it was at the end of the previous step, hydrogen, hydrogen, draw out my alkyl group, and then plug in my positive formal charge right here. And now for our base, to grab a proton from this rhenium acid, we will use aluminum tetrachloride because we need to remove a chlorine atom from aluminum tetrachloride to restore it back to aluminum trichloride, the catalyst of the reaction. So we have to recreate that catalyst. And so in order to accomplish that, put that negative charge on our aluminum there. The bond between aluminum and chlorine is weak. It breaks. The electrons from that come over with the chlorine atom to form a bond to the proton here, making HCl. That forces that hydrogen-carbon bond to break. The electrons from that come down to restore the aromaticity. So we'll go ahead and create our 6-membered ring here. Conjugated all the way around. Hydrogen here. Then I go ahead and plug in my 3-carbon group, 2 methyl groups there at the first position right here. And that is also going to result, we'll create products, aluminum trichloride, restoring our catalyst. And I'll also go ahead and write out our HCl, which would be the other product of this reaction. So our major organic product going to correspond to this rearranged product right here, where we've rearranged relative to the starting alkyl halide structure. So be on the lookout when you are doing Friedel-Crafts alkylation reactions that there can be carbocation rearrangements. That's something that you need to think about when you're writing out the products of these reactions, that you may want to draw out at least part of the mechanism, particularly this first part here, even if you're only asked to write out the final product of the reaction, because it's at this first part of the reaction mechanism that will make it clear whether you need to rearrange the carbocation or not. And if you do need to rearrange the carbocation, you're going to attach that rearranged carbocation via the positively charged carbon onto the aromatic molecule in the final product. So do keep that in mind as you're going through these so that you come to the correct constitutional isomer product rather than creating a product that does not have the necessary rearrangement.